Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So in this video, I would like to answer some of questions from our follower, which is Jahid Akhtar said commented on the video. Can you explain the calculation of diffusion coefficient from CV curve? So for disclaimer, I'm not very knowledgeable on the diffusion coefficient, but I will try to explain a little bit information on the diffusion coefficient. Okay, so let's see if my explanation help you. It's one small step for me and a giant leap for the mankind. So we just sharing the knowledge. So hopefully you can take the knowledge and also read from other sources also to gain more knowledge into the diffusion coefficient. Okay, let's see some introduction. So in the context of supercapacitor and cyclic voltammetry, CV, the diffusion coefficient plays an important or a crucial role in understanding the performance and the behavior of the supercapacitor. So we are talking about coefficient diffusion, which represent how quickly the ions move through the electrolyte in response to the applied electrical field. Because when we are using potentiostat, we apply the current or the voltage and we want to see how fast the ion move from the electrolyte to our electrode, either in the surface or the bulk of the electrode. So in the case of supercapacitor, diffusion coefficient, the letter T, indicates the rate at which ion can transport to or ion can be transported from the electrode surface during charging and discharging process. So that's the keywords of diffusion coefficient. We want to see the rate of reaction between the ion transported from the electrolyte or to the electrolyte. So it's vice versa during charging and discharging process. So CV is a common electrochemical technique used to study the redox behavior and capacitive properties of the electrode. In a CV experiment, the potential applied to the electrode is we vary our potential applied, okay, correct, and the resulting current response is measured. Okay, so in the CV, we set, for example, our potential window from 0 to 1 at different. So what we give the potential. So we measured the current. That's why from the CV, if you can see, the y-axis is your current response, while the x-axis is the potential versus the standard reference electrode if you are using 3-electrode system. So this technique provides information about the kinetic and reversibility of the electrochemical reaction occurring at the electrode-electrolyte interface. In CV experiment on the supercapacitor, the peak current observed in the cyclic voltammetry are directly related to the diffusion of ion and from the electrode surface. So that's why when you observe a very intense redox fix, that's why it's necessary for you to calculate the diffusion coefficient. For example, in capacitor, we have EDLC, we have pseudocapacitor, and we also have battery type. So the most cases that people use to calculate diffusion coefficient when they deal with supercapacitor, when they are dealing with obvious anodic and cathodic peaks. That's why in this case, the peak current that you observe during the cyclic voltammetry is directly related to the diffusion of ion to the electrode surface or from the electrode surface. During the forward scan, or we call that oxidation or charging process, so the ion diffuse into the electrolyte from the electrolyte to the electrode surface, resulting increase in the current until maximum peak current. We call that IP. And vice versa, during this charging or reduction process, ion diffuse away from the electrode surface, leading to reduce in the current. So it's a vice versa process. Okay, a little bit about fact about the diffusion coefficient. So we have the relationship between the IP and D and other experimental parameter is described using one equation. The name of equation is Randles-Sevcik equation. So you might heard about this when you are researching on the diffusion coefficient. Okay, this equation relates the peak current, the scan rate, the number of electrons, the electron transfer, electron surface area, and diffusion coefficient and other constant in one relation. So let's see, this is the relation, the Randles-Sevcik equation. We got the IP equal to 2.69 times 10 to the power of 5 times with the number of electrons, power 3, power of half times with the electrode surface area, then diffusion coefficient power of half times with the concentration of the electroactive species, and times with scan rate power of half. Okay, this is the Randles-Sevcik equation that you need to dive into when you are dealing with diffusion coefficient. So to solve the D, to find the D value, you need to rearrange and you can get equation like this one. D equal to IP divided by other constant. So results of interpretation, how to interpret the diffusion coefficient. So it's quite easy. A higher diffusion coefficient, the higher the D value, the faster the electron transport and the better the ion accessibility to the electrode surface, leading to higher peak current in the C vehicles. Conversely, a lower diffusion coefficient implies to slower electron transport, which can result in lower peak current and reduced charge storage capacity. So, by understanding the D value of supercapacitor through CV, allow us to optimize our electrode material, electrolyte composition, device architecture to enhance ion transport, kinetic, and overall supercapacitor performance. So basically, in a nutshell, we want to have high diffusion coefficient value to have high or faster electron or ion transport. So to simplify, because it's quite a complex equation, so how to simplify the equation? So just plot the IP, the peak current versus square root of scan rate. So we can get one correlation in terms of y equal to mx plus c. So we can use a linear regression to calculate the diffusion coefficient. So just plot the IP versus scan rate power half. So when you plot like this, you can get y equal to mx plus c. So IP is the peak current, x is your scan rate power half, and m is your gradient. From the linear regression, you can get the value of m, the gradient, in which related to the D, diffusion coefficient. And what you need to do, the gradient value, you need to divide by the constant. 2.69 times 10 to the power 5 times the number of electrons times the surface area and also times the concentration of electroactive species. So let's do some example. You might be curious, a lot of equation, a lot of terms. So let's do some example. So for example, we already run the cyclic voltammetry and we already plot IP versus scan rate of power half. So we draw the linear regression. You can get a linear regression. So after you get a linear regression, you determine the value of the slope. For example, in this case, 0.7 and the y-intercept 0.1. So you need to do your experiment and find the value. So after that, what you need to do, you need to define. So how many number of electrons involved? If one, state 1. If 2, state 2. Then you need to define the surface area. So if your electrode, the surface area is 1 centimeter square, just put 1. And the concentration of electroactive species, how many molar? So everything you need to define first. Then after that, okay, then you can calculate the D value. So just put the gradient divide by all these constant parameter. Then you got your D value in terms of centimeter square per second because it is a rate you measure in terms of time. That's why centimeter square per second. So let's see some graph example to convince you about the coefficient, diffusion coefficient. Okay, normally people are calculating the diffusion coefficient when they are dealing with sensor because sensor dealing with the redox potential during the CV. So in this case, how to read the graph? So the first graph and the second graph. they already plot the peak current versus carried power half. So as a layman, at first sight, how to determine which one is good? Okay, let's see. Let me open the pointer. Okay, from this graph, which one is good? The good one is here, the red color, because red color produces the bigger red gradient. The bigger the gradients means that the bigger the D value. The bigger the D value means that the faster the ion transport. So same goes for the rest. You find the bigger gradients means that you got the bigger value, the faster the ion transport. So in summary, the gradient of the Randles-Sevcik plot provides valuable information about the diffusion kinetic in the system. A high gradient indicates efficient ion transport and high diffusion coefficient. A low gradient suggests lower electron transport and a lower diffusion coefficient. So from this, you can discuss more your performance in terms of supercapacitor reaction.